Welcome back to the second part of Lecture 4 of our course, Introduction to Complex and Algebraic Geometry. In part 1 of Lecture 4, we started discussing Poincare dbar Lemma. We are going to do a quick review and continue from there. So, a very quick review of Poincare dbar Lemma. We started from a very simple problem in calculus. We said, suppose a function g from R to R is given. And suppose this function is smooth and integrable and has all good properties. And suppose we are looking for another function, looking for a function f from R to R, so that the function f satisfies the following equation. Derivative of f at any point x is equal to g of x. Right. So here g is given, and f is the unknown. Right. And it's easy to solve this equation. So one can see f at any point x is given by integral of g. So we introduce an integral variable t, and then we fix the base point, say 0, and then integral of g of t dt from 0 to x would be a solution. There are other solutions for any constant c, we would get another solution, right? And the reason is that if I define f using this formula, if I take derivative would kind of cancel with the integral, c would disappear, and you just get g of x at the end. Now, we were discussing a complex version of this one. So in the previous lecture, we started to consider the complex version of this problem. So when we have functions from c to c, we can consider the same thing rather than r to r. The essential thing here is that in this problem, we were taking derivative of f with respect to x, right? Over complex numbers, we could take derivative with respect to z, the complex variable, we could take derivative with respect to z bar. And actually, this was the version we were considering. We were considering the case where we have a function g given from c to c, and we were looking for a function f from c to c, so that derivative of f with respect to z bar is equal to the given function g. So at any point z, we have this equality. So this is the complex version, right? And we kind of considered a slightly simpler version where g is defined on a bounded domain u inside c. And let's say it's smooth. So also we say g from u inside c to c is given. So it's given. Let's say we are assuming g is smooth. This is the notation for the smoothness. Let's say it's bounded. It's essentially the notation for bounded. We wanted to say then there is a function f defined on the same domain so that f satisfies this equation, right? That was the main thing. So this is our theorem. And we spent most of part 1 of lecture 4 to kind of find an expression for f, at least be able to guess what f is. So what we learned or almost guessed is that there is a function f satisfying this equation given by the formula. So motivated by the real version, we could kind of guess f is given by an integral of g. But what is that exact integral? So we learned the integral is integral over u, g of some variable of integral w divided by w minus z, d of w edge, d of w bar, up to a constant, 1 over 2 pi I. Right, so this is the theorem, and this is called Poincare dbar Lemma. Right. Okay, now we want to prove that. And proving it is essentially a matter of computation, because when we have an expression for f, we kind of guessed it. But now that we have an expression, so in order to prove, we should just essentially take derivative of f with respect to z bar and check if it's equal to g or not, right? So it's more like a computation rather than Very abstract proof, right? So we are going to do that. Now we want to do this. So first attempt to prove this. We want to take derivative of f with respect to z bar at any point z inside u and see if it's equal to g or not. So the question is that at the end, can we get this is equal to g of z or not? So we are taking derivative with respect to z bar, and the theorem said f is given by 1 over 2 pi integral over u g of w over w minus z dw wedge dw bar. Okay, derivative is with respect to z bar, the integral is with respect to w, so we can interchange them. Also, we have good assumptions on g, so there is no problem in doing that. So this is equal to 1 over 2 pi I integral over u. In fact, g is also in w, so it would act as a constant for the derivative. We have derivative with respect to z bar of 1 over w minus z dw wedge dw bar. So what is derivative of 1 over w minus z with respect to z bar? What is this derivative? That's the main thing. The point is that w again is like a constant here. So the variable there is z. What is the derivative of z, 1 over z with respect to z bar? So this is a bit tricky, so a bit of digression here. When w is not equal to z, it's a well-defined thing. The denominator is holomorphic. It's non-zero, so 1 over w minus z is well-defined. In that setup, 1 over w minus z is a holomorphic function. And remember, derivative with respect to z bar of any holomorphic function is 0. So in that case, derivative with respect to z bar of 1 over w minus z is equal to 0. But when w is equal to z, there is singularity. We have 1 over 0. So taking derivative is problematic. So what does it really mean? When w is equal to z, it's more like 1 over 0 thing, which is kind of like an infinity. And this fits into the notion of distributions. So this is more like a distribution rather than a function. This actually is related to something called Dirac's delta function. So the value of this derivative as a distribution would be 2 pi I Dirac's delta function, which is now a function of w centered at z. This simply means when w is not equal to z, this is 0. But however, it's really concentrated at the point z. And it's exactly defined, so this is the value of what we have inside the box. And the definition of Dirac's delta function, is exactly the following. It's the thing that if you multiply it with any other function, here g, and integrate it, it would be equal to the value of that function at the base point. So here, note that 2 pi I cancels 1 over 2 pi I, so we have integral of g times Dirac's delta function, and this would be exactly the value of g at the base point, which is z. So we get what we wanted. However, I know this is not a very satisfying proof, especially if you are not familiar with Dirac's delta function. So let's try to find a more kind of down-to-earth proof. However, this time I'm going to add a simplifying assumption. This assumption is not necessary. I'm just adding this assumption to simplify the problem. We can remove that easily. So I'm going to add assumptions. So suppose G, which was defined on some bounded region U inside C to C, I'm assuming it has compact support inside U. So this is C. This was our set U. I'm going to assume outside of some region inside U, compact region inside open set U, maybe it's better to denote it this way, some region inside U. Outside of that is equal to 0. So I'm assuming G is equal to 0 outside of this red region. Okay, in particular, G is 0 on the boundary. The reason I assuming that is that, then I can extend G in a smooth way to the whole plane C. So I define G of Z to be 0 when Z is an element of C minus U. So I just define G to be 0 outside of that. It's because G is 0 outside of a compact region inside the open set U. When I'm doing that, I have a smooth extension of G to the whole plane. Okay? Okay. So that's just the assumption I'm adding. You can remove that and prove the theorem without that. That's just a simplifying assumption. Okay, now with that assumption, let's try to compute derivative of f with respect to z bar directly. So the formula said f is given by this integral dw wedge dw bar. Now, since g is 0 outside of u, I can slightly change the integral, and rather than u, replace the integral over the whole plane C. Because for any point which is not inside U, G would be equal to 0, right? So it does not have any contribution to the integral. So these two things are equal, right? So let's say 1 over 2 pi I, integral over C, derivative with respect to Z bar of G of W over W minus Z. D of W wedge, D of W bar. Now, this is a bit tricky. The whole point is just playing with variables. Note that here, the function is defined with respect to z, which we would also see here. The derivative is with respect to z bar, which we also see here. The integral is defined with respect to w, which we see here and here. So w is living inside u. Now I'm going to define a new variable u to be w minus z. And since it's a complex valued variable, it would always be equal to some r e to some I theta. I some theta, right? So this is just u definitionally. I define u to be w minus z, and it has an expression of the form r e to the I theta. Now let's use that and rewrite the integral. So this integral would be equal to 1 over 2 pi I, still integral over whole c, derivative with respect to z bar. Now, g of w would be equal to, what is w from here? W is equal to z plus r e to the I theta, right? What is w minus the denominator? It's r e to the I theta. D of w wedge d of w bar. So this should appear here. It might be a bit tricky to compute d of w. The trick is that w is the variable of the integral. For the integral, z is like a constant. Z is not variable of the integral. So d of z here would vanish, would be 0. R and theta, on the other hand, are the variables of the integral. So this would be d of r e to the I theta. And then w bar would be d of r e to the minus I theta. So you should use the product rule. There would be dr times e to the I theta plus d of e to the I theta, then there's the R, etc. I let you compute these, compute the W wedge dw bar, see what is the final result. It would be minus 2RI dr wedge d theta. Okay, if you do the computation correctly, you would get that. And then this is equal to, well, I and I would cancel it, 2 and 2 would cancel. We get minus 1 over pi integral over c, and derivative with respect to z bar of g of z plus r e to the I theta. E to the I theta can come out of the integral because derivative, sorry, can come out of the derivative because we're taking derivative with respect to z bar. So we would have e to the minus I theta dr d theta. Hopefully there's no sign mistake or anything. Okay, so the essential thing is that I should compute this. What is this? What is inside is z plus r e to the I theta, which is w. So what I have inside is derivative of g of w with respect to z bar. This is very simple, but might be a bit confusing. So note that if I think about the function g as a function of w and w as a function of z itself, the derivative with respect to z bar is essentially the same as derivative of g with respect to w bar. The reason is that derivative of g with respect to w bar is derivative of g with respect to z times derivative of z with respect to w bar plus derivative of g with respect to z bar, derivative of z bar with respect to w bar. This is essentially chain rule written in the complex coordinates. So what is derivative of z with respect to w bar? We had w is equal to z plus r e to the I theta. So w bar is equal to z bar plus r e to the minus I theta. So z bar is equal to w bar minus r e to the minus I theta. And also z is equal to w minus r e to I theta. So if I take derivative of z, which is here, with respect to w bar, well, there is no w bar there, so this is 0. And if I take derivative of z bar with respect to w bar, z bar with respect to w bar would be the coefficient of w bar, which is 1. So this is 0, this is 1, which is derivative of g with respect to z bar. So they are equal. I mean, this is pretty straightforward, right? So going back, this is the whole thing is equal to derivative of g with respect to w bar. So let's call the whole thing star. Now, star is equal to minus 1 over pi integral over c g derivative of g with respect to w bar. And then we have e to the minus I theta dr d theta. Okay, now we can rewrite everything back in terms of w and z. So this would be equal to d of w wedge d of w bar divided by w minus c with some constant, which come here and make this 1 over 2 pi I. And then we have this integral here. So this is almost like the Cauchy's integral formula if you look carefully. However, Cauchy's integral formula had another term. Cauchy's integral formula was like, if you have this plus 1 over 2 pi I integral on the boundary of u of g of w divided by w minus z dw, which I'm correct, the whole thing would be equal to g of z. Also, if instead of c we had u. But the point is that this is fine. Why? Well, integral over c and u are the same because g is 0 outside of u, so those integral are equal. Also, g is equal to 0 on the boundary, so the whole integral here is equal to 0. I can add 0 to this. So by Cauchy's integral formula, the whole expression is equal to g of z. Remember, we started from derivative of f with respect to z bar at the point z, and then we got g of z, which is great. We just had one simplifying assumption that g vanishes on the boundary. If we didn't have that, this would have been more challenging, right? What can we do when that's not the case? In fact, in the book by Griffiths and Harris, they don't have that assumption. You can go and take a look. This is a good exercise. You can think about it yourself and you can see how you can prove it in general case. Now that you know the proof in the case where G has compact support inside you.